All right, in this problem, 25, we're looking at successive ionization energies. So this is demonstrating the amount of energy required to remove the first electron, the second, the third, the fourth. And so when trying to determine or decipher the difference between these numbers on a table, what we're looking for is the significant jump. So from one to the next, we're looking for a very large gap in the numbers. That's going to signify the difference between removing valence electrons and core electrons. So that'll help us determine. And since it says these are in the third period, we know that these are all going to be elements that go across, this way here. So let's take a look and see what we have. The first one, 496, and all right off the bat, that's like 9 times greater. This one's less than double, so we have a large jump here between the first and the second, which means we could easily remove 1 but not 2. What element could we remove 1 but not 2 in the third period? That would be sodium, because you have 1 valence electron. When it gets rid of it, it's like neon. Then you have that stable octet. So the best answer for that one is sodium. Okay, let's see here. We have double, and then like maybe 5 times greater, and that's less than double. So here is our jump between the second and the third. So which element could we remove 2 but not 3 from? That would be magnesium. You could remove this one, you could remove this one, but then when you get over here to neon, you're filling that, or you're breaking into that core, those core electrons, that there are 8 of them. Okay, this is like 3 times greater. That's like less than double. Then all of a sudden, like 4 times greater. There's your big jump between the third and the fourth. If it's between the third and the fourth, it's going to be aluminum, because it has 3 valence electrons. You can remove 3 but not 4. So that would be aluminum. That's how you solve that guy. All right. Ionization energy measures the ease at which an atom loses an electron, whereas electron affinity measures the ease at which an atom gains an electron. Circle the one that has the higher electronegativity value. So remember, electronegativity is the strength of an atom's pull on a shared pair of electrons in a chemical bond. And so in looking at this, fluorine is the most electronegative element. The closer you get to fluorine, the more electronegative you are. So electronegativity increases going this way. So your least electronegatives are down here, your most electronegatives are over here. And the noble gases don't have electronegativities because they don't share. They don't form compounds. And so the general rule of thumb is the closer an element is to fluorine, the more electronegative it is. Fluorine has an electronegativity of 4.0. And if they're equidistant, so let's say oxygen and chlorine, I want to know which one is more electronegative. They're both one space away. It's the one with the smaller radius. Okay, because there's less core electrons to block. So that's the general rule of electronegativity and how it works. And so fluorine is the most electronegative element. And looking at carbon or nitrogen, nitrogen is closer than carbon, so it's nitrogen. Magnesium or neon, so even though neon is right next to it, it's one of those noble gases, so it doesn't have an electronegativity. It has its perfect collection, magnesium in that case. And then arsenic or calcium, once again, arsenic is right here, way closer to fluorine than calcium is. And so it is going to be arsenic. Explain why electronegativity increases as you go across a period but decreases as you go down a group. Okay, so here we go. Electronegativity, we said it decreases, and we'll say it increases going across. The reason why, as you go down a group, the valence electrons are getting further and further from the nucleus. There's more shielding from the core electrons. As you go left to right across a period, electronegativity increases because your ZF, your effective nuclear charge, is greater, and you're getting closer to an octet. This is just some additional electronegativity problems. Oxygen closer to fluorine. Fluorine is the most electronegative element. Oxygen is the second most electronegative element. Sulfur is more electronegative than potassium for the same reasons. Properties of metals and nonmetals. Let's sort them out. So we're going to go metals over here and over here. And nonmetals. Okay, so some things that metals, properties metals have. They tend to be shiny or reflect light. They are lustrous. That's another name for shinies. They are lustrous. They are malleable. Malleable means bendy. Metals are ductile, which means you can pull out and they turn into a wire. They're found on the left side of the periodic table. They're all really good conductors of heat and electricity. They're mostly all solids at room temperature. And they're mostly silver or gray in color. There are a couple like copper and gold that are copper and gold colors, but mostly silver or gray. Properties of nonmetals. Okay, they're the opposite of shiny. They're dull. They're not very reflective. They're the opposite of malleable, which is brittle. They tend to fracture. They are not malleable. They're found on the right side of the periodic table. They tend to be poor conductors of heat and electricity. You find them in all three states of matter. So solid, liquid, gas. And, that's it. They tend to, and then the ones that are solid, the colors, they tend to be brightly colored. Unless they're gases, then they're invisible. Okay, so this next part, we're identifying elements. So elements that are a metalloid. So remember, metalloids are ones that are going to touch the stairs. Oops, I want to go this way. So the ones that touch the stair step here. So anything that touches the stair step with a side is going to be a metalloid. Aluminum doesn't count. So really, any of these can count. So like boron, silicon, arsenic, tellurium, germanium, antimony, all those count. Transition metals. Transition metals, holy schmoly. Anything in this area is a transition metal. The things in groups 3 through 12. So anything in here. Not these down here because they're called inner transitions or lanthanide and actinides. But there's a whole bunch of them you could list. Anything in that D block, essentially. So we're just going to put various. If I ask you one on the test, you tell me one, but I'm not writing out 40 elements. Okay, an alkali metal. Alkali metals are anything that are here in this group. The only one that isn't is hydrogen. So any of these other than hydrogen would work, which would be lithium, sodium, potassium, rubidium, cesium, francium, any of those count. Okay? A halogen. Halogens are these, group 17 elements. So any of those count as a halogen. So you could put things like fluorine, chlorine, bromine, iodine, astatine, any of those count. This one's asking for a very specific element, an alkaline earth metal in the second period. So you have to look at first, alkaline earth metals are right here. Second period is this guy. The answer has to be beryllium. Okay, so it doesn't have a lot of choices. It has to be beryllium. The next one, a noble gas in the fifth period. Same thing, very specific element. Okay, so 1, 2, 3, 4, 5. This is the fifth period. Noble gases over here, group 18. It is xenon. The member of the most reactive nonmetal group. Okay, so the most reactive nonmetal is going to be somewhere over here, the halogens, right? So once again, these are very reactive. They have 7 valence. They want 8. So it's something in there. So any of the following could be fluorine, chlorine, bromine, iodine, astatine, any of those. Remember the most reactive metal groups? Okay, that's going to be the alkali metals because they have 1 valence. They want to get rid of them, so not hydrogen, but anything else in that group would count. So anything between lithium, sodium, potassium, rubidium, cesium, francium, any of those. The most electronegative alkali metal, okay? The most electronegative alkali metal would have to be this one, lithium. The number of elements in the alkali metal family, 1, 2, 3, 4, 5, 6. Hydrogen is not one of them. So there are 6. Oops, I went the wrong way. The largest alkaline earth metal, well, that's going to be the alkaline earth metal at the bottom. So the one at the bottom should be radium. The halogen with the lowest ionization energy. So halogens are here. Lowest ionization energy, I would assume you'd put astatine. You could probably put tennessine, and that would count, but astatine is sufficient. The smallest element with 4 energy levels. So 4 energy levels implies it's in the 4th period. Go across, the smallest one is krypton. The most electronegative transition metal. Well, transition metals are here. It's going to be the one closest to fluorine, which is probably zinc. The largest atom in the 2nd period. So once again, 2nd period is here. They get smaller going across, so the largest one is lithium. And then the smallest element that has 3 valence electrons. So that would be something in this group. The smallest one would be boron. Okay, explain at least 3 uses of radioactivity in the world is the next question. And so there are various answers to this. These are some of those. So we talked about atomic weapons, weapons of mass destruction. We talked about nuclear power plants and using them to generate electricity, so making steam to turn the turbines in a power plant. We talked about smoke detectors, how they use radioactive americium to detect when there's particulate matter in the air, like in smoke. We talked about medicine, treatments of cancers. Talked about tracers, where they can inject you with radioactive dye so they can track blood flow in your body. They can see if certain nutrients are being absorbed, like, for example, to see if your thyroid is functioning. They can see if it's taking up iodine, stuff like that. In agriculture, they can use tracers to track plants' ability to absorb nutrients from the soil. They can track things like pesticides and herbicides and see them being picked up by plants and seeing if they're being transmitted on to animals that eat those plants. So many answers for explaining uses of radioactivity in our everyday lives.